All right. Let's get started for today. Looks like everyone was busy programming last night in particular, and maybe not everyone has recovered yet. Congratulations on finishing your first assignment, your first bigger project in C, if you haven't programmed in C before. Do notice, however, that you can still late submit, everyone who hasn't submitted. I checked just before the lecture. I've received 282 submissions so far, which means there's about 25 missing. There will be no late submissions accepted after this coming Sunday, and this simply means, as you know, there is a cap of 15% for every day late, and that will then run out next Sunday. If you've already submitted, please be mindful that you're not supposed to show your code to anyone, not even after the deadline. And one of the reasons is that people can still submit their assignments, and you don't want to get yourself into trouble. Now, as for marking, I will obviously have to wait until Sunday to receive all late submissions. And then the plan is to run auto-marking, auto-testing next Monday. But then, of course, we will have to manually look at all the programs that have been submitted to check on style, to check on the complexity. And with over 300 programs, this is obviously going to take a few days. So I can't promise anything, but if possible, we try to be as quick as possible. We might have the marking out by the end of week 7, if not, then sometime during week 8. Now, we will start looking at one particular type of data structures that will keep us busy for the next 3 lectures. We will be looking at graph data structures and a first type of algorithms. Today, graph search. And then we will be looking at many more graph algorithms next week. Plus, next week we will have an in-class fun quiz here in the class. You can win fame and prizes. And all this is in preparation for the online midterm test that will happen in week 8. You don't have to prepare for the in-class fun quiz next week. Just be here and be ready to answer a few questions on either your laptop or your mobile phone that I will be posting here, just in preparation of the test. Before we're going to start today, let me introduce someone else to you. The next in a series on famous computer scientists. What this person invented affects your life, I'm sure, every single day. Does anyone know who he is? I think last time you were very good at recognizing Alan Turing. Who is he? Not really Wi-Fi, no, but it's getting closer. What do you use Wi-Fi for mostly? Yeah, on your phone, but what do you do with your phone when you... Internet, yes. So he invented the internet. This is Tim Berners-Lee, Sir Tim Berners-Lee, I should say, who is an Oxford computer science graduate, who was a software engineer in Switzerland. And when he was a software engineer at that institution, he invented the first version of the web. He was a founder and director of the W3 committee at MIT. And why is he attributed with having invented the web? He invented distributed hypertext, texts on different machines, and adding links to these texts that were linking heterogeneous documents with each other. And this is what the World Wide Web is all about. He also invented the Universal Naming Scheme, also known as URL, the Basic Transfer Protocol, HTTP. What I found interesting is he was visiting UNSW just a few years ago, and he gave a very interesting talk on the early days. For example, he apologized for this initial pair of slashes that at least previously you had to type in HTTP:// before you can enter the web address. And he said it had no real meaning, and he didn't even remember why he invented it. It was just a nuisance for everyone later. You typically don't have to do that anymore. You can just type www dot something, but he used the 2 slashes just so that it differs from other addresses that you type in. What I also found very interesting is that in hindsight, he says that he should have defined web addresses the other way around. So instead of saying cse.unsw.edu.au, which we are so familiar with now, it would have been more logical to do it in this way, to have the highest level domain come first. And why is that? Because if you then get deeper into a file structure, you do the same thing. You start with the outermost directory, and then you go deeper into the directory. So it would have been much more logical if we were to type in web addresses in this way nowadays. But it's far too late. Obviously, everyone's got used to it. And there won't be any changes in that anymore. Interesting enough, also, for having invented the web, he won the Turing Award in 2016, just 2 years ago, which is, as I said last week, named after Alan Turing, whom we met last week, and is considered the Nobel Prize for computer scientists. Now, here's an image of the first idea of the web. And you can see there were different types of documents that he had, and he wanted, or he proposed to link them together. And this is all the documents that he had at the beginning. The World Wide Web today, obviously, is much, much larger, but this was the original idea. The reason why I'm introducing this also for today's lecture is that when we start talking about graphs, we will see that one very important application of graphs and graph data structures and graph algorithms is to analyze structures such as the World Wide Web with the help of graph algorithms. You can see that the way this is being depicted here, it is obviously a graph. You have nodes and you have edges or arrows between these nodes. And in general, you can consider every link on a web page that links one web page to another web page as the web pages themselves are nodes in a graph, and these links denote edges in the graph. And companies like Google, they use lots of graph data structures and algorithms to analyze the link structure of web pages. Other companies like Facebook, they look at social network graphs where, for example, every user is a node in the graph, and every friend of a user, for every friend you have an edge between these two users, and then they analyze the structure of those graphs. So this is why we will be looking at graphs, and I will begin with a few very basic concepts for graphs before we then started looking how we can encode graphs on our computer as abstract data types, and then what type of algorithms we can apply to them. Now, graphs are almost everywhere. Very often, as we will see with some of the problems that we will be looking at later, you might not even recognize a problem immediately as a graph problem, but when you think about how to best encode and solve it, then very often it's very natural to consider it to be a graph problem. What we generally have when we talk about a graph or graph problem is we have a collection of items, a set, for example, of elements, and we have relationships or connections between these items. Very simple examples where it becomes very obvious that we have a graph is you have maps. Items are cities or road maps for a specific city. Then items would be intersections. And you have connections between intersections that are roads. The web pages can be considered items in a graph. And the connections between items are hyperlinks when one web page links to another web page. Collections that we have already looked at are lists, linear sequences of items. We looked at this in our course in week 4, and of course you know that from Comp 9021. You would also have looked at trees, branched hierarchies of items in 9021. We will be looking at trees a little later in this course again. Graphs are more general because they do allow arbitrary connections, not just linear connections, and not just these hierarchical connections as in trees, but just arbitrary connections between items. So when we speak about a graph, we consider a set of vertices, let's call it V, and we consider a set of edges that connect two vertices with each other. Every edge, therefore, is a subset of the cross product V times V, because we select one vertex and a second vertex and we connect them. And then we might obtain a very simple graph like this, which consists of 4 vertices, here numbered V1 to V4, and we have edges E1 to E5. And you can see that every edge connects exactly 2 vertices. I'm going to show you a real example here. Australian road distances. Here we have major cities. And then we have road distances between them. And you can see that the road distances here are given in full for every connected pair. You see vertices are cities and also edges that are here denoting distances between cities. They are also symmetric. You can see that the distance between Darwin and Canberra is 4441. I suspect this is kilometers. And the same you have for Darwin to Canberra. If you look at other graphs, flight times, for example, average flight time, that might be different because it might depend on whether you're flying east or west, and then you wouldn't have a symmetric connection. For the time being, we will only consider these symmetric connections between vertices of a graph, and later we will be looking at what is known as directed graphs. Now we can provide an alternative representation of the above and show a diagram which illustrates these connections between the individual cities. Now here you don't have all these connections, so this is only part of that graph that we had in the matrix before. Now this is typically easier for humans to appreciate. At least if we have a small graph, then it's always nice to depict a graph in this way. On a computer, obviously, we will find or have to find a representation that might be closer to the representation that we have here, but there are alternative ways in which we can encode or represent a graph as a data type, and we will be looking at several possibilities later today in this lecture. Now, what are typical questions that we ask about a given graph? We may, for instance, be interested in, is there a way to get from item A to item B? And depending on the application, this might have a very different meaning in a specific application, but these very different meanings to find a path or a way from A to B then can all be answered by looking at the graph and trying to see whether we can find a collection of edges that takes us from A to B. We might wonder what is the best way to get from A to B. Whatever best means, it might be the shortest way in terms of the number of edges, but it might also be the shortest way in terms of the distance or in terms of the flight time. We might wonder which items are connected. In a social graph, you might ask the question whether you may not know person A does not know person B personally, but maybe there's a connection of mutual friends. And then you wonder whether there is a connection between these two items in a graph. Graph algorithms, they tend to be more complex than tree or list algorithms. And that's got to do with the fact that we don't have an implicit order of items. In a linear list, it's very easy. We can linearly traverse a list, whereas traversing a graph, as we will see towards the end of today's lecture, is a bit more involved. Graphs also may contain cycles, and you have to make sure that if you search for an element, that you don't end up running in a cycle and never get to the element that you're looking for. The concrete representation is less obvious also. How do we represent a graph on a computer? We will look at 3 different ways to do this. And there's no best way. It really depends on the type of graph that you're looking at, which representation is more suitable. Also, the algorithm complexity may depend on the so-called connection complexity. Do we have relatively few vertices and lots of edges between these vertices, or do we have what is known as a sparse graph, many, many vertices and relatively few edges. And the algorithm complexity then may really depend on what type of graph you're looking at. A little bit more about the terminology. When we ask the question how complex an algorithm will be for the specific problem that we want to solve, such as finding a path from A to B, we normally answer that question in terms of how big the graph is. And when we talk about how big the graph is, there are two components that are of interest. How many vertices do you have, and how many edges? So the cardinality of these two sets is really very important. And for the sake of simplicity, one normally doesn't even use the cardinality, the official mathematical cardinality notation, to indicate that I'm interested in the size of that vertex set or the edge set. We just write V and E. And you will see later how I'm going to use this to characterize the complexity of algorithms. Now, a graph that has V vertices can have at most V times V minus 1 divided by 2 edges between them. But the ratio, the number of edges versus the number of vertices, can vary considerably. If your number of edges is closer to V square, like we had in our road distance example, we had lots of edges and relatively few vertices, then we call this graph a dense graph. If E is much closer to V, so we might have more edges than we have vertices, but the order is roughly the same, then we call a graph sparse. And the distinction between dense graphs and sparse graphs is really very important because it comes down to when you select an algorithm or even a data structure to begin with to represent a graph, it comes down to the question whether your graph is more on the dense side or more on the sparse side. And sometimes you have a very different representation that is suitable or more suitable for one case rather than the other. A very good example for a sparse graph would be web pages and hyperlinks. There are billions of web pages, and every web page has maybe a dozen or a few dozen at most links. So we don't have that almost all web pages are connected to almost all other web pages, which you would typically have in a dense graph, but this is very, very sparse. And if you want to represent something like this at Google, when they analyze their web pages and the graph that represents the connections, then they will always choose, I'm sure, representations that are suitable for sparse graphs and algorithms suitable for sparse graphs. So as I said, it's really very important to know when you do an application in which category the graphs fall, because it does affect the choice of the data structure to represent the graph, and it may affect the choice of the algorithm to process a graph, depending on what you want to do with your graph. The edges in a graph represent pairs of connected vertices, as we have seen. For an edge, we always select an element of V times V, or V square. So if we have a set of 5 vertices, then we have all these possible pairs to consider, selecting one vertex from the set and another vertex from that set to form all possible pairs. Now, obviously, if we've got 5 vertices here, we would have 25 elements in this set, V square. Why do we say that the maximum number of edges, which I said on the previous slide, is not V square, but V times V minus 1 divided by 2? Any idea why it's not V square? Because we have V square pairs, obviously. But why do we have fewer edges to consider?
Because the vertex don't need to link to itself.
Yes, that's right. So we will not consider loops. That is, we will not consider vertices like 1, 1. That would actually then give us V times V minus 1 edges. And why do I divide it by 2?
You're not counting the same edge twice.
I'm not counting the same edge twice if it's not directed. Later on, we will be looking at directed graphs, and then this is getting closer to V square. If we then also allow loops, then we actually have v squared, but for the time being, that's exactly right. This is why we have fewer, because VW and WV, these are ordered pairs, but they denote the same edge in an undirected graph, and for the time being, we don't want to consider loops. Now, a bit more on graph terminology. For an edge E that connects two vertices, V and W, we say that V and W are adjacent. This is the technical term, and you will see me use that term a lot. It, in principle, means they are neighbors. They are linked by an edge. I'm also going to sometimes use the technical term that E is incident on both V and W. The degree of a vertex is then defined as the number of edges incident on E. No, that can't be right. It actually should say V. Please correct that. The number of edges incident on V. So you're looking at a particular node V, and then you count the number of edges that are connecting V to any other vertex. I'll make sure that I correct that. This is the degree, and obviously in a very dense graph, the degree of a node would be close to the number of vertices in the entire graph, and in a very sparse graph, the degree would be relatively small. When we look at the web pages and consider hyperlinks as links, then the degree of a particular web page would be the number of links that go out or in, if we do not distinguish between directed edges. Now, what I will be used as synonyms is you can either call a vertex, or you can call it a node. There is no real distinction between that. It's only that vertex comes from Latin and node is a Germanic word, and you have that very often in English, that you have these two words from these two origins. And in graphs, we can really use them interchangeably. Edges is what I will usually call the connections between two vertices. Sometimes I call them links, sometimes I call them arcs. As a note, however, I should mention that some people do make a strict distinction between arcs as directed edges and edge as undirected edges. What else do we have? A path is a sequence of vertices where each vertex has an edge to its predecessor. And a cycle is a path where the last vertex is the same as the vertex that you started with. Now, this is quite simple. We will see an example here. The length of a path or a cycle is just defined as the number of edges that are being needed for the path. So here we do have a path 1, 2, 3, 4. The length is 3 because we need exactly 3 edges. And of course, you have another path 4, 3, 2, 1. Here we have a cycle. We can start at any vertex and just go around once, and then we have a cycle which obviously is of length 4 because we need exactly 4 edges. So that's all very straightforward and I suppose very intuitive. We are also interested in finding out whether a graph is connected or not. Connected means that there is a path from every vertex to every other vertex. And if a graph is not connected, that is, you can find at least 2 vertices where you can't get from A to B, then this graph is not connected and has at least 2 or more connected components. That is, subgraphs that are connected, but these individual subgraphs are separate from each other, and you can't get from one node in one subgraph to another node in the other subgraph. Then we sometimes refer to the so-called complete graphs, also known as K subscript V, where V is a number, the number of vertices that you've got, and they are defined as the densest graphs that you can build with V vertices. there is an edge from each vertex to every other vertex. And so in a complete graph, the number of edges is really the maximum, v times v minus 1 divided by 2. So here you have an example. This graph consists of 6 nodes, and every node is connected to every other node. So you've got 6 divided by 2, which is 3, times 5, 15 edges in total. I think these are, for the time being, the last few concepts that I'm introducing. A tree is defined as a connected subgraph, which has no cycles. And here we have one example. This is a tree. There's one and only one way to get from one vertex to every other vertex, because there's no cycle. So-called spanning tree, and these will be very important because they're very interesting applications where one has to build spanning trees out of a graph. This would be a tree that contains all vertices of a graph. So if you look at just this graph here, consisting of the nodes 13 to 17, and you look at the green edges, then this is a subgraph. It contains all the vertices, but only some of these edges. And this would be called a spanning tree of that graph. As I said, it's really very important. We will be looking at some algorithms to compute these spanning trees because many applications require you to do this. Finally, a clique is a complete subgraph. That is, if you're looking at, for example, this graph here, and you look at these 4 nodes here, and you can see they are all connected pairwise, and this is why they are called a clique. In this case, we could also say a clique of size 4 because we have 4 nodes that are connected to each other. And again, it's an interesting problem and important for practical applications to find such cliques. I'm sure that Facebook, for instance, is very interested in finding groups of people that are that satisfy the property that everyone is a friend of everyone else. And they might be interested in finding large cliques, and they might even try to find groups of people, that is, groups of nodes, which almost but not quite form a clique. And then they will send you an email and tell you that all your friends know this person X, why don't you befriend that person as well? And that you can easily find out by looking for sets of nodes that are almost but not quite cliques. Now, if we consider this entire graph, then we can first of all see, simply because I've numbered them easily, that there are 26 nodes in that entire graph. If you want to count all these edges, there are 32 edges, and you can see there are 4 connected components. The entire graph with all the 26 nodes is obviously not connected, but we have these 4 individual connected components. And what I should also say is that the entire graph doesn't have a spanning tree. That is, you cannot find a subgraph which forms a tree. What you see here is a spanning tree only of that particular component. And what you can build is what is known as a spanning forest, which would be spanning trees for every individual component. That's what I've defined here. A spanning tree, just formally, is a subgraph that contains all vertices and some edges so that you obtain a tree. So it must still be connected, but is not allowed to contain any cycles. And a spanning forest of a graph that consists of 2 or more connected components would be a subgraph of G, again, containing all the vertices, and is then a set of trees that themselves are not connected and have no cycles, so that you have exactly one tree for each connected component. All right, let's see if you paid attention. Here's our graph with the 4 vertices again and 5 edges. If I want to build a spanning tree for that graph, how many edges do I have to remove? 3? Well, if I were to remove 3 edges, then yes, one of these vertices will definitely become disconnected. So if I remove E2, E3, and E5, then V3 will be disconnected. And as a matter of fact, yes, I can only remove 2, and then I would obtain a spanning tree. How many different spanning trees can I construct for this particular graph? How many different spanning trees? $13? That's a few too many. 10 is a good attempt. That comes close, but it's not quite right. So I assume that you said 10 because we have to remove 2 edges. And there's exactly 10 possible combinations. If we have 5 edges, then there's 10 possible combinations of edges. But not every combination would give you a spanning tree. Why is that? That's very good. Yes, some combinations would make it unconnected. If, for example, I remove E1 and E2, then I obtain this triangle here, but V2 would be disconnected. Does that make sense? So you can't remove E1 and E2 together. So of the 10 possibilities, that leaves us with 9. Is there any other possible combination that wouldn't work? E3, E4, yes. If I take E3 and E4, that also wouldn't work because then V4 would be isolated. Any other combination? No, that's it. Every other combination would work, and therefore I've got 10 minus those 2, 8 different spanning trees, which is one of the interesting properties, that there are very, very many different spanning trees. This is a very, very small graph. And we already have 8 spanning trees in total. So later on, when we look at trying to find minimum spanning trees, which is what people typically look for, and I will define what minimum then means, the number of possible spanning trees might be a problem. And this is why one needs smart algorithms that don't just consider all possible combinations of edges that can be removed. But for the time being, yes, this is right. So we have 2 edges that need to be removed. And of the 10 possible ways of removing 2 edges, 8 would lead to an actual spanning tree. All right, almost done with the introduction. We have already said that for the time being, we will be looking at graphs where we don't consider the order. When we look at edges between the 2 vertices, so an edge from U to V would be the exact same thing as an edge from V to U. And we also don't consider self-loops. We don't have an edge V to V. This is what is known as an undirected graph. And that is opposed to a directed graph, which we will be looking at in later lectures, where the 2 edges are really different. And you have to indicate what the direction is. Often with directed graphs, you also consider self-loops. And here are 2 very simple examples, an undirected graph. And here we have a directed graph, and you can see that in some cases you have an edge or an arc in both directions, and in many other cases you have an arc only in one direction. And you can see different applications. If you befriend someone on Facebook and this is mutual, then this would be a symmetric graph. If you look at Twitter and they look at who follows whom, then this would always be represented by a directed graph, because if A follows B doesn't necessarily mean that B also follows A. Other types of graphs that we will be looking at are weighted graphs, where each edge has an associated value. which is generally called the weight. And the weight can have many, many different meanings. It can, for example, on a road map, denote the distances between cities. When you use Google Maps and you try to find the fastest way from A to B, then it actually does not only take into account the distance, but also the average speed with which you can travel on a certain road. And then you might even prefer longer roads if you can drive faster, which is why you typically get a different path when you distinguish between driving from A to B or cycling from A to B, or even walking from A to B. So these weights in general are very important for those graphs. In other graphs, they might denote the capacity if your graph edges represent pipes, for instance, or any other connections between two nodes. And then these weights become also very important. Finally, let me mention the concept of so-called multi-graphs, where you even allow multiple edges between two vertices. We won't be looking at those, but you can extend the general definition of a graph and some algorithms to allow that as well. For example, when you want to analyze, or when people analyze larger programs and how functions depend on each other, then you might build the so-called function call graph, where you have an arc, a directed edge, from F to G if F calls G, and if F calls G at several places, then you might want to distinguish these different places from each other, and then you have multiple arcs between the same two nodes. But this is very special, and we won't be looking at those types of graphs. So that was my introduction to graph terminology, and now let's have a look at possible ways in which we can represent graphs as data structures when we want to implement them on a computer and implement algorithms on them. When you want to define a graph, then you obviously need some way of identifying vertices and edges between them. One way, and this is the way that I've been showing most of the graphs so far, was to give a diagram that shows the edges and the vertices. Another possibility would be to say what the vertices are and then just list the edges one after the other. So here are different representations of exactly the same undirected graph. You see that here we have one drawing that is very different from this drawing here, just as a drawing, but it denotes exactly the same graph. You have the same set of vertices numbered from 1 to 5, and you would have edges between the same pairs of vertices as in this diagram here. Then here we have a list of all the edges arranged in such a way that in the first line we have all the edges from 1 to any other node in the graph, then from 2, from 3, and from 4. And we could just list these edges, and it would give us the complete information if we know that the vertices are the numbers 1 to 5. It would denote exactly the same graph that we have depicted here. Then we can rearrange these edges, and we can turn them around. And again, they are ordered by edges going from 1 to another node. And then instead of having 1, 2, I've denoted 2, 1 here. And since we don't want to distinguish in undirected graphs between an edge 1 to 2 and 2 to 1, this would be the exact same as the edge that I've denoted here. So they are different. They are denoted differently and rearranged here, but it's exactly the same graph, again represented in this way. Now what we will be looking at is three different graph data structures, common data structures that can be used for different purposes. They are known as array of edges, which is just like the representation that we've seen on the previous slide. We just enumerate all the edges in a graph. And then we will be looking at the so-called adjacency matrix representation and contrast that with the adjacency list representation. Now these two are the most common in practice. And as we will see, it really depends on the type of graph that you have and the type of procedures or algorithms or operations that you want to have, that you have to perform on these graphs, which of these two is the preferred one. Now let's start with the simplest representation first, where we take edges and represent them as just an array of edge values. So we define what we mean by an edge. Obviously, it's pairs of vertices, and we somehow have to encode this. And then we say we just use an array that lists all these edges. An advantage of doing this is that this is space efficient, more space efficient than other representations, as we will see. The disadvantage is that adding and deleting edges is slightly more complex than in other representations, as we will also see. When we use an array of edges for encoding an undirected graph, then the order of vertices in an edge, a pair of vertices, doesn't matter, as we have seen, whereas if we have directed graphs, then the orders do matter, because they then, the order does matter because we then use it to encode the direction. So here's a very simple example. We have a graph with 4 nodes and 4 edges. One representation would then be using an array like this of 4 elements containing these 4 edges, pairs of vertices. Here we have the same number of vertices, and we have directed edges now. We have, for example, this loop here. And you can see now here, whereas it wouldn't make a difference whether we have 2,3 or 3,2 in this array, here it does make a difference. We have to use 2,3 because we have the edge in this direction. And we have that self loop, which is represented by that 1,1 pair in that array. Now, throughout this course, for simplicity, we will always assume, just like I've done here, that vertices are numbered from 0 to the number of vertices minus 1. And that just makes encoding much easier, and talking about these graphs also easier in all these examples. In reality, obviously, you would have more information with a vertex. It would not necessarily just be numbered, but it would be associated with some contents, just like we had linked lists, not only of integers, but in our assignment, a linked list element was more than just an integer. It was a whole transport card record. And in practical applications for graphs, we often have that as well, that these individual vertices are more than just a label and contain information. But for all the algorithms that we will be looking at, for simplicity, we will always assume that we use these numbers from 0 to the number of vertices minus 1. So when we now look at pseudocode, how we could implement that idea of array of edges, then we will see that pseudocode is really very simple, because this is one of the very straightforward implementations, and there's absolutely nothing surprising or difficult in this pseudocode for the various basic graph operations. Let's start with creating a new graph. Suppose you want to build an abstract data type where a client can build a new graph, just like they could use or build a list or a stack previously. Then we require the client to say that they want to build a new graph with V nodes. And therefore, the input would be the number of nodes or vertices in the graph, and the output would be an empty graph. Now, setting that up is very simple. You might want to use a field for a struct nv, which counts the number of vertices in your graph, which would be initialized by v, the number of vertices that you have. And since this is an empty graph, you might have another field that counts the number of edges, which would be 0. Then if we want to build this as an abstract data type, we would have to decide to allocate dynamic memory for the array of edges. The big question is how much should we allocate? This here just says allocate enough memory. What is enough? Definitely no more than, if we have undirected graphs, v times v minus 1 divided by 2. We know that this is the maximum number of edges. If you have a very large graph with lots of vertices, let's say 100,000, then 100,000 square is a very large number. And therefore, you would need much less in practice, in particular if you're dealing with a sparse graph. Of course, you might then run into problems that you haven't allocated enough memory, and if then the client wants to add one more edge, you would have to allocate more memory and copy all the information over. So that's the initialization. All we need is one array that has enough space for all the edges that we might want to add. What do we do to add an edge? That's very simple. With an array of edges, we take, I shouldn't have said I here because we have to know what I is. We have to put in the vertex, VW. So first of all, the insert edge means we want to insert an edge, VW, into a graph. What we do know is the number of edges that we currently have. So if we start to fill the array from the beginning, then if the graph is empty, the number NE, that counts the number of edges, would be 0. And then when we add our first edge, we would put it into index 0. So instead of just saying I should have made clear in that pseudocode that I is actually that number GNE, the number of edges that we currently have. And then we increment it by 1 afterwards. So I'll make sure that I correct that as well. Do replace that I by g.ne. It's the first index that is now available in exactly the same way we have used an array for a stack of elements. So that's very easily done, edge insertion, assuming that we don't have to check whether the edge is already in the array. If the edge is already in the array, then it's not a good idea to increment the number of edges and just put the edge into the array again, because then when we remove it, we would have to check for duplicates. So this pseudocode would work only if we can be sure that inserting an edge will only be called if an edge is not already present in the graph. Edge removal then requires exactly that. And I suppose this is where the I came from. Now, if you want to remove an edge from an array of edges, you have to start at the beginning and you have to find the edge in order to remove it. So you start at index 0 and then perform this while loop that looks for this particular edge. And as long as it hasn't found the edge, it increments I. And then when the while loop ends, we can be sure that index I is now indicating where the element, the edge that we want to delete, can be found. And deleting itself then is pretty easy. We can, instead of moving all the edges one index down, because we don't have to order these elements, we can take just the last edge at the very end of the array and copy it to the place where we delete our current edge. This is what happens here. You just take the last existing element and move it down into that index element where you now have space for that last edge. And you decrement the number of edges so that you know that all the edges that might still be at higher indices are no longer valid. So that's not really easy because in the worst case, it does require you to go through all the edges, and it might be the very last edge in the array that needs to be deleted. And this is why this can be a costly operation, in particular if you have a large graph with many, many edges. So when we look at the cost of these different operations, then we will see, well, first of all, you will see that I'm using the notation that we introduced last week, the big O notation. Instead of saying exactly what the cost is, we give an estimate, and we just say what is the order of the cost that we can expect. And you can see that we can do that not only with the time, but we can also do that with the space, how much memory is required in general to represent a graph in a particular way, for example, using this array of edges. And you can see that then the size of the graph will be measured, at least in this particular case, when we define or determine the storage cost, will be measured in terms of how many edges do I have. Independent of how many vertices I have, the storage cost will always be in the order of the number of edges because I've got that array of edges. And if I have a huge graph with millions of, let's say, Facebook users, but only very few edges, then the number of vertices doesn't really matter. I only have the array of edges, and therefore the storage cost only depends on the number of edges. And obviously it's linear in the number of edges. Now the cost of the operations is initialization is constant. Creating a new graph is straightforward. Inserting an edge is also very easy. You just add this one edge at the end of the array. And this can be done in constant time as well, because you don't have to go through the array under the assumption that the edge array has space. If you run out of space and you have to reallocate memory, then you have to copy all the elements over. And that might then require a time complexity in the order of E. But just inserting an edge is constant. This is why it's very efficient. On the other hand, finding and deleting an edge, we've already seen that in the worst case, just to check if there is a connection between node A and node B, you might have to go through the entire array of edges. And of course, you have to do that when you delete an edge, which is why this requires in the order of the number of edges time. If the array is full on insert, we've already seen allocate space for a bigger array and copy edges across, requires time linear in the number of edges. What you can do is you could try to maintain the edges in order. And if you do this, then we can use what we've also seen last week, much faster search to find an element and to delete an element, namely binary search. You don't have to go linearly through that array. You can just jump into the middle, and then depending on where the edge is located to the left or the right, it will be much faster to insert or to find an edge. And if you can do this, then the complexity reduces to logarithmic of the number of edges. And this is so much better than linear. If you assume that you have an array of edges representation, how would you show a graph? How would you output all the edges in a graph? What would be a very simple way of printing a graph with an array of edges? It's really very simple. Anyone? Yeah. So it is extremely simple. If you have an array of edges, outputting the graph is just looping through the array of edges and printing every edge. I'm saying this here because we will look at other representations where it's not as straightforward. But for an array of edges representation, it really is very simple. You loop through the edges, you just print them. The time complexity of doing this, showing the entire graph, will obviously also be linear in the number of edges. And again, for other representations, we will see later that the time complexity is going to change, which will show that depending on the representation, different operations have different time complexity. Here, this is really very easy. You just have that loop to print all these edges. And I think that brings us to the next representation, where rather than having an array of edges, we use what is known as the adjacency matrix representation. This might be, if you've ever used graphs and implemented them, might be the more natural thing to do. where you represent the edges by a square matrix, a V by V matrix, that in a graph where you have 4 edges, 4 vertices labeled 0 to 3, would give you a 4 by 4 matrix like this. In an undirected graph, it would be symmetric, and you would have a 1 in that adjacency matrix whenever these 2 vertices are adjacent. That is, there is an edge between them. In an undirected graph, this matrix, or this relation, would be symmetric. Whenever you've got a 1 here, you would have a 1 here, and whenever you don't have an edge here, you also don't have an edge here. In a directed graph, this relation would no longer be symmetric, and the 1s in that adjacency matrix, they would indicate the direction. So putting a 1 here means we have an edge, an arc, from 0 to 3, as we see here, but we don't have one from 3 to 0, and therefore this entire matrix is not symmetric. Let's have a quick look at advantages and disadvantages of doing this. One advantage is that this is even easier to implement than the array of edges by using a 2-dimensional array. It's very, very simple, and this is why this is probably the most natural representation of a graph. Another advantage is that you can represent not only graphs and directed graphs, but you can also very easily represent weighted graphs. And the difference would then be for standard graphs, undirected, you would have a symmetric Boolean matrix. Boolean, because you have either 1s or 0s. There is an edge or there's no edge. For digraphs, which is the standard name for directed graphs, you would have a non-symmetric Boolean matrix, as we have seen on the previous slide. You still have 0s and 1s, but you might have a 0 for the entry AB and a 1 for the entry BA. And for weighted graphs that are directed, you would have a non-symmetric matrix of weight values. Instead of just having 0 and 1s, you can easily insert a weight for a particular edge. Like the matrix that we've seen at the very beginning with the road distances. That was a matrix representation where we had the different Australian cities, and we had the distance between pairs of cities. Now, these are all advantages. There is one big disadvantage, and that is if you have only very few edges, that is, you have a very sparse graph, then this is very memory inefficient. And why is that the case? If you look at this matrix and you assume this is much, much larger, you have hundreds or thousands of nodes, and you have only very few edges in your, relatively few edges in your graph, then almost all these entries would be 0s, and only a few would be 1s, and therefore you would waste a lot of space compared to other representations, including the array of edges. And this is why this representation is memory inefficient for sparse graphs and wouldn't be the method of choice if you want to analyze Facebook connection graphs or web hyperlink graphs. But for many other applications where it is not sparse, this wouldn't be necessarily memory inefficient or require much more storage space than other representations. Let me quickly go through the same operations, basic operations, before I will have a break, and then before we look at the third possible representation. Graph initialization would now be a little more complex because you have to allocate the memory for the entire matrix. Again, we would have that if the user wants a graph with V vertices, the number of vertices will be V, the number of edges will initially be 0. You would allocate memory for the matrix. Here it's very clear how much memory you have to allocate. It's just that two-dimensional matrix. And then you have to initialize it by a for loop that sets all the entries in the matrix to 0 to make clear that there's no connection between any two vertices. So that's a bit more complicated than the initialization that we had for the array of edges, where we basically didn't have to do anything. On the other hand, edge insertion and edge deletion, as you can imagine, is extremely simple. To add an edge to the graph, we now here even check whether the edge doesn't already exist. It doesn't exist if the current entry is 0, and if we have an undirected graph, we want to make sure that both directions are recorded. So we say that the matrix element VW and the matrix element WV is set to true or to 1, and we have one more edge in the graph. So that's very simple, and unlike in the array of edges, it's equally simple to remove an edge from the graph by checking that the edge is there and then setting the corresponding matrix elements to 0 and removing 1 from the number of edges. Now this is obviously much simpler than removing an edge from the array of edges representation, where in the worst case you had to go through all the edges, which is why for edge removal and obviously also for checking adjacency, just checking whether there is an edge between A and B or V and W, is extremely easy in that representation, whereas in the array of edges it was much harder. Now the question again is, if you want to display a graph that has been encoded in this way, how would you do that? So again, we want to know, for example, all the edges in a graph. What would be your approach to do that? Just like in the previous example, where this show graph algorithm should display all the edges in the graph, which was very simple. We just had that loop going through the array of edges and printing every element. How would we achieve the same result here? Anyone? Again, it's not too difficult. Given a matrix, how would you print all the edges? So suppose that this is what you have stored in your computer, and you want to output all edges in that graph. Yes, that's exactly right. And then do what?
And then if matrix ij is 1, and then
yes, so that's exactly right. You go through the entire matrix, but as you said, it suffices for an undirected graph to go through only one of these halves, the triangles. And whenever you find a 1, you output the corresponding edge. That's exactly right. This is what you can do here. And there are different ways of doing this. Here I've used even I and j as you suggested. I start at 0 to nv minus 2. And why is that? If I don't have loops, then I know there will never be a 1 in the I entry. And then what have I used here? I used the upper right triangle. I think you suggested to use the lower left, but that, of course, doesn't make a difference at all. And if g edges is true, that is non-zero, then I'm outputting that edge. To indicate that there is an edge from I to j, I might do it in this way. Now, if we look at the time complexity of this is very different from the time complexity that we had previously. Previously, outputting all edges had the obvious time complexity linear in the number of edges if you go through the array. Here we have these two nested loops that loop through the number of vertices. And this is why the time complexity is OV square. That is, it doesn't depend on the number of edges at all. It only depends on the number of vertices, and it's quadratic in the number of vertices. This is roughly the same if we have a dense graph. Remember, in a dense graph, we have approximately as many edges as we have v squared, because the maximum number of edges was v times v minus 1 divided by 2, which is in the order of v squared. But if we have a very sparse graph, this will take much longer than printing just a few edges in our edge array. So when you look at the storage costs and the time complexity of the adjacency matrix representation, what can you say about the storage cost? How much memory do you need for an adjacency matrix? In the order of v squared, yes, v squared, which again is very different from the order E that we had for the space for adjacency matrices. Initialization, how much time does that take? Also v squared, yes, and that's because we had these two loops here which had to set all the entries to 0. Again, this is very different to the constant initialization that we had previously. Insertion is constant. Yes? It is constant, yep. So this is just basically these, we can count the 2 or 3 operations that you have to do. Removal, it's also constant, and that's the big advantage as opposed to the adjacency array of edges representation, where it was linear in the number of edges. And show graph, we've already said this is OV squared. And I think this was all we had. So the storage cost is OV squared. If the graph is sparse, this is not a very good representation because most storage will be wasted. And the cost of the operations are, as we just said, OV squared for initialization. But then the big advantage is insertion and deletion only, or can be done in constant time. So if you have a dense graph where you very often have to check to insert or to delete an edge, then this is a very nice representation because it doesn't waste too much storage, and it can be done in constant time. And with this, I think it's about time to have a break. Give me 7 minutes, and we will restart at 7:20, and then look at the third and final representation. I forgot.
For the mid-semester, is that date going to change, or is that already locked in?
Okay. Let's continue here. One interesting question that I got was if you, in the array of edges, if you keep the edges in order, would the insert also require log n? Well, it would require log n to find the place to insert an edge, but it then would require to move all these edges to the right, and that might take linear time as well. If you have to insert your new edge at the very beginning, then everything has to shift to the right. So it wouldn't really make it more efficient if you use a linear array, which is why this representation is very easy to implement, but probably not used in practice. The one that we will be looking at now is probably the by far most popular and most common representation if you have a sparse graph. If you have a dense graph, it's these adjacency matrix representations that are typically being used. What was the other question that I got? Why did the printing or show graph loop only went from 0 for the outermost loop to nv minus 2 and not nv minus 1? The reason is that you don't have to look at the last row at all, because all the edges that are encoded in the last row, they will already be printed going through the last column. And this is why the outermost loop can stop at nv minus 2. If we have 4 nodes, it can stop at 2. There was one question that we looked at the time complexity. Then we looked at this. There was one more thing that has already been alluded to. You can use a slightly more efficient way if you have an undirected graph. Then you don't have to duplicate every entry in that matrix. You can only store the top right half of the matrix. And you could do it in this way. Instead of having a V by V matrix, you would have a slightly more complex graph representation. You count the number of vertices, you count the number of edges, and then to store only the upper right triangle, you might have an array of 3 elements, assuming we have 4 nodes. For the first row, then you only need 2 elements for the second row, 1 element for the third row, and you don't have to represent anything for the last row, because everything, just like I said, will be represented in the upper right triangle. Now, the storage cost for this would be, you need v minus 1 pointers. Why v minus 1? Because you don't really need the last pointer here. And then only half the ints. This is still OB square. Although you have only half the numbers, it's still in the order of square, because if you calculate this, this is still square in the number of vertices. It also requires good bookkeeping. You always have to use edges VW, so that V is smaller than W, so that you can be sure you only use the upper right triangle. I won't go deeper into this, but there's a very nice exercise in this week's homework, which looks a bit closer at this representation and asks the question, how do you actually compute where to find a particular element in this more efficient representation? Now, the last representation that we are looking at is most suitable for graphs that are very sparse. And the idea here is that for every vertex in your graph, you store a linked list of all these vertices, all the vertices that are adjacent to a particular vertex. So if we look at this undirected graph and we use this concept of the so-called adjacency list representation, then we see that 0 is connected to 2 vertices, 1 and 3. And this is why the list associated with vertex 0 contains the 2 elements 1 and 3. There is 2 vertices adjacent to 1, namely 0 and 3, and this is why we have this list. 2 has only 1 vertex adjacent to it, namely 3, and 3 is connected to all other vertices. This is why it has this list 0, 1, 2. this for an undirected graph, you can see that every edge is represented twice. The edge from 3 to 1, for example, you have the entry 3 for the adjacency list for 0. And for the edge 3, 0, you have 0 in the adjacency list for 3. For an undirected graph, you can use the exact same idea and then only put a vertex into the adjacency list of another vertex if there is an arc from that vertex to this vertex. So we've got 0 to 3, and this is why 3 is in the adjacency list for node 0, but not the other way around. So that's the so-called adjacency list representation. Every node has its own adjacency list, which collects all the vertices it is adjacent to. This is probably the farthest from this graphical depiction, but it is a representation that can be very efficient, in particular for sparse graphs, as we will see when we look at the individual operations. Now, advantages are that it might be a little more difficult to understand than the array of edges or the matrix representation, but it is still relatively easy to implement in languages like C in particular, where we can use linked lists for these lists of adjacent vertices. Another advantage, as we've just seen, is it can represent graphs and directed graphs, undirected graphs and directed graphs. And it is very memory efficient in case the ratio between the number of edges and the number of vertices is relatively small, because we are now back to the O in the order of the number of edges and not OV square in the number of these vertices squared. One disadvantage is that one graph may have many possible representations unless the lists are ordered using the same criterion, as in you order the vertices just by their index, if we number the vertices from 0 to nv minus 1. But otherwise, if you were just to add elements to the adjacency list, then you wouldn't distinguish between different orders in which these vertices are listed in the adjacency list. And as I said, then there are many different ways to represent the same graph. That wouldn't happen in the adjacency matrix representation. There's one and only one adjacency matrix that would correspond to the graph that you want to represent. Now, what would we have to do to initialize a graph when we use the idea of adjacency lists? As before, obviously the number of vertices is v, the number of edges at the beginning is 0. And then you want to allocate memory for the nv minus 1, oh no, actually nv lists that you need. That is, you need pointers to these lists. And all these pointers will be initialized with the null pointer, or generally with what indicates an empty list. So you would have an array of list pointers, now speaking about the C implementation, and all these pointers would be 0 at the beginning because all the adjacency lists will be empty. Inserting an edge would now require to use standard list operations. If we represent or encode this adjacency list with the help of linked lists, then adding an edge would require 2 insertions into a linked list. We would have to insert vertex W into the adjacency list for vertex V, and we enter V into the adjacency list for node W. And for this, we would use standard insert linked list operations. Edge removal is almost the same. Now we have to remove an edge, means we have to remove a vertex V from the adjacency list of W and the other way around. We could use a standard delete linked list operation that removes an element from a linked list. and reduces the number of edges by 1, obviously. So if we look at the storage cost and the time complexity of the adjacency list representation, what do you think we need in terms of space if you consider this linked list representation? Now, of course, speaking in general terms, we have a graph with V vertices and E edges. How much space, how much memory do we need for this representation? In terms of V and E. V square or E square? Did you say V square or E square? V square. No, that's not quite right. It's not necessarily V square. Suppose the graph is empty and you have 100,000 nodes. Then you don't really need 100,000 times 100,000. You only need that if the graph is really full. That is, if you have V square edges. Then the answer would be right. But in general, if we want to express this in terms of the number of vertices and number of edges, it's not V square.
When you ask that question, aren't you asking from the point of view of worst case scenario?
Yes, I'm asking about the worst case scenario, but depending on 2 parameters. And one parameter is V and the other parameter is E. If I were to ask for the worst case only depending on V, then you would first of all have to find out what the worst case of a graph is. And that would indeed have V square edges. And then the answer would be correct. It would be V square. But if I now ask what is the complexity in terms of 2 parameters, then you can take both parameters into account. And then this answer, then you have to say what is the, there's probably no worst case. If you know the number of vertices and the number of edges, you know exactly how much space you need. Yes? V plus E square. Why V plus? Yes, this is correct. So you need V, you need these list pointers for every vertex, plus E square. Why E square? You have every edge twice. But if you have every edge twice, does it really require E square? 2 times E. And this, fortunately, is much less than E square. So E square would be if you have all the combinations of these edges, but 2 times E is just the same as E. And this is why the answer then is correct. It is, the correct answer is OV plus E. You need, in the order of the number of vertices for these vectors, and in the order of the number of edges memory here. If you have a very dense graph, coming back to what you said, then O of E becomes the same as O of V square. And then the memory that is required is V plus V square, which is the same as V square. That is for dense graphs. The memory requirement is the same as for adjacency matrices. But if you have a very sparse graph where E is much smaller than V square, then you only need OV plus E. Okay, very good. Initialization takes or requires how much time? V? Yes, it's linear in the number of vertices. We've got that one loop here that initializes the vertex, the adjacency lists to 0 for every vertex. And this is why it requires OV time. And what about edge insertion? Constant. That is correct, yes. To insert an element into a linked list, if we don't order it, you just add it at the head of the list. And this can be done in constant time, as we know. This is the advantage of using this linked list, because then adding it is just a constant operation. What about removal? Is that also constant? No, because you have to find, in order to delete an element in a linked list, you have to go through that linked list. So it is indeed not constant, but what is it? Linear, quadratic, logarithmic? Linear in V or in E? In E. Is that really true? Why not?
Maybe one node cannot contain all edges.
That is exactly right. So the adjacency list is bound by the number of vertices. You cannot have more elements in your linked list than you have vertices in the graph. So it would be bound by the number of vertices instead of edges. And typically, even in sparse graphs, you have more edges in total than you have vertices, because otherwise you would have a tree or something that is very disconnected. So that linked list that you have here, that is bound by the number of vertices. And this is why the correct answer to the question, what is the time complexity for deletion or even finding checking whether two vertices are adjacent, is OV, linear in the number of vertices. And I think this is all we had. So this summarizes what you just said. Everyone together, the storage cost is OV plus E. You need V pointers to the lists and a total of 2 times E list elements, which is of the order of E. And initialization is OV. Inserting an edge is constant, as you rightly said, assuming that we don't have to check for duplicates. If you want to make sure that you don't have duplicates, then you would have to find whether an element is already in the list, and that would then require OV time, just like finding or deleting an edge. If the vertex lists are sorted, then if you really have a linked list, insert would require a search of the list, because you can't insert the element at the beginning. You want to keep the vertex list sorted, so that would then make it into an OV algorithm as well. And deletion, as we have said, always requires a search, regardless of whether the list is ordered or not, and therefore will always require OV time. So all this is really very interesting, because it tells us that there is no one unique way, most efficient way of representing a graph. It really depends on the type of graphs that you need to be looking at in a particular application. So if we summarize all that we have said so far, then we see that the adjacency matrix, in particular in a sparse graph, wastes a lot of memory, because the space usage is V square, whereas it's only V plus E for an adjacency list, and even better for an array of edges. Initialization for an array of edges is really extremely simple. It's just constant. On the other hand, you don't initialize a graph too often, and therefore the actual operations on a graph might be more important. Inserting an edge is efficient in all cases. Finding an edge, that is checking whether two vertices are adjacent, is having a complexity of OE, which is really very bad if you have a large graph. If you have to very often find or delete an edge, then this is certainly not a good representation. Adjacency matrices are extremely efficient in that regard. Adjacency lists, they do work if you have a very sparse graph where the degree of a node is very small. Remember that degree is the number of edges incident And if you have small degrees, then that limits the size of the linked list. And then even this operation wouldn't be too costly. Let me have a quick look at other operations, some of which we will be looking in much more detail, where you also see that algorithms that you write for specific problems have very different complexity depending on which representation you use. For instance, to check whether a node is disconnected from every other node in a graph might take a very long time in an array of edges representation, but it's extremely fast with an adjacency list representation because you just have to check whether the adjacency list of that node is empty. A very simple check, and that can be done in constant time. Whereas to check that the entire row for a vertex contains zeros does require to go through the entire row in an adjacency matrix. What is an extremely important problem, and we will be looking at it in the third hour of today's lecture, is to check whether there is a path from X to Y. And we see that for all three representations, we do get different complexities. So again, for that question, it might matter a lot which of these representations you choose, depending on the structure of the graph. And finally, copying a graph, that is copying all the elements, has this complexity, and destroying a graph, that is deallocating, freeing all the memory, is very simple with an array of edges. Is only one free operation, whereas for the adjacency matrix and adjacency list, it requires a bit of work. But again, this is not a standard operation that you would do very often, so this probably doesn't matter that much. All right, now we have seen these three different representations. Now let's have a quick look at how we can implement all three different representations using all the methods that we looked at in C as an abstract data type for graphs. Now, for an abstract data type, the data that we want to deal with are obviously sets of edges and sets of vertices. And the standard operations are just the ones that we looked at: building a graph by creating an empty graph and adding edges, then deleting edges, removing an edge, or freeing the memory that has been occupied by an element of this graph abstract data type, and scanning is a very standard operation, which asks the question, if we have two vertices, X and Y, are they connected or not by an edge? Things to note for the graph abstract data type that I'm introducing now and that we will be using in this course are that we won't change the number of vertices of a graph. So all we need to say is at the beginning, when we initialize a graph, how many vertices do we have? For many applications, of course, this is not realistic, and you also want to add and remove vertices from and to a graph. But for our purpose, our graph abstract data type fixes the number of vertices, just to make it simpler. And to make it simpler still, we treat vertices as integers. But of course, in reality, in many applications, they are not just numbered, but they will contain actual information. For all the algorithms we will look at, we can ignore all this, and we say that vertices are not complex structs, but they are just identified by integers. So that what we will build is this as the graph abstract data type interface. We define the data type graph as a pointer to an undefined struct, in the same way we do that with linked lists. I define the type vertex, but it's just an int. Here I'm defining the struct edge using that double definition, so that there are two different ways in which I can define edges, consisting of just a pair of integers with the field v and the field w. And these are the operations. Adding or creating a new graph inserting an edge, removing an edge. Then adjacent is the function to scan a graph. We want to check whether or not there is an edge between two vertices, and the answer should just be yes or no, which is why I'm giving this the type bool for Boolean. As we know in C, bool is just a value that is either 0 or not 0, true or false. False always is encoded as 0, true encoded as 1. But from now on, in all my C programs, I will use this extra type bool to make clear that here I'm representing a truth value and not just a random general integer. And freeing a graph obviously means that I want to destroy all the memory that has been occupied for a graph. So adjacent, in particular, is the question, is there an edge between two vertices? Now, assuming that I have these operations, let's have a look at a simple exercise where I want to write a client that uses this graph abstract data type for a very simple problem. I want to build the graph depicted below, this simple graph here, and then I want to print all the nodes that are incident to vertex 1, that are connected to vertex 1 in ascending order. So suppose you have to do it. You want to build this graph, and then you want to print all the nodes adjacent to 1 using just these operations that we have here. How would you do that? What would be the first thing that you would do? Take a new graph. Yes, so we have the new graph operation or function for this. What would be the argument? Do you remember what the graph was? So we have 4 nodes here, so the argument will be new graph 4. And then you want to build this graph with all these edges. What would you do for this purpose? Insert edge, yes. So you take the graph that was returned by that new graph constructor, and then in order to add a specific edge, you would have to construct a specific edge using these two fields, V and W, and you would just go through the edges that you have and add them. And lastly, to print all the vertices that are adjacent to vertex 1. How would you do that? Printing all vertices that are connected to 1 with the help of these functions. Anyone? Yes? Two for loops. From 0 to 2.
And the second one is start from the variable in the first loop and to the last vertex 3. And if the adjacent is 2, and print the edges.
Okay, so that would print all the edges, right? But the problem was I didn't want to print all the edges. I just wanted to print all the vertices that are connected to 1. So with 2 for loops, you would print just all connections, but I'm only interested in those connected to 1.
Use just one loop and go through all the vertex and check them if the adjacent graph 1 and the vertex is 2 and 3.
Correct. Yes, this is exactly what you do. You use just one loop and then check whether this is adjacent to 1, and that gives you, and then you print it if the answer is true. That's exactly right, and I've done that here. So this is my graph abstract data type. There's one function that I haven't used on the slide yet, but I've added it to the program because it will come in handy later, namely to get the number of vertices in a graph. It just returns the value that has been used to initialize a graph. And I've also added showGraph as a function that outputs the entire graph in a specific way depending on what the underlying representation is that I'm using. So that's my interface, and this is the graph tester, and it now does exactly what we have said. We first of all, the number of nodes in this particular case is 5. So this is not exactly this graph. It's a slightly different graph that I have been using here for a tester. And then I'm defining E as an edge. Edges consist of 2 values, V and W. And I've got exactly 4 edges that I'm adding here. Then I'm using showGraph in this particular tester. And I'm using a few more edges to remove and to see what the result is. And as I'm saying this, I realize this is not exactly the program that I was asking for here. So let me go back to this and just show you what the corresponding program would have been. But the one that I implemented is slightly different. I will go back to it in just a second. So this is what we said. We create a graph with 4 nodes. We insert all 4 edges in the graph that we had. And then we have that one loop that goes through all the nodes, checks whether any of these nodes is connected to our particular node of interest, which in this case is 1. And then it prints just that node V if it really happens to be adjacent to 1. And that's all we have to do. Never forget to free the memory that has been allocated for a particular abstract data type before you return. So that's that very simple program. And now let me go back to the other program that does a bit more. It creates another graph, slightly different. It has 4 edges also. But when you look at these edges more closely, you will see that there's one edge that is duplicated, namely 1, 3 and 3, 1. So if I have an abstract data type implementation that takes care of not duplicating an entry, then the resulting graph should contain exactly 3 edges. And here I'm removing edges. And again, you will see there's one edge, namely from 4 to 1, the last one that I try to remove, which is not actually in the graph. And if I, again, implement the underlying abstract data type correctly for this function remove edge, then this shouldn't reduce the number of edges. But this is generally how you can use the client that we call graph.h. And before I'm going to show you the implementations, let me just run it, and let me tell you that there is one particular make file that I have created for all 3 different representations. So I've built 3 representations, implementations for 3 different representations: the array of edges, the adjacency matrix, and adjacency list. And here I just make, you can make a difference, what you want to test. So the graph tester here would use the graph array of edges implementation. This one would use one that I just called graph. And I call it graph because this is the one that we will be using not only today, but for the next 2 lectures, which is the adjacency matrix representation. And the third one is the list of edges representation. And you can see that requires yet another abstract data type, namely that linked list implementation. And before I'm going to show you the actual implementation, let me just make one which uses the array of edges. for the graph tester. The result will be nothing. And that's because it's just called test, the executable. So you see we have the 5 vertices, we have the 3 edges, and in the array of edges implementation, it just outputs the edges one after the other. Removing the edges takes care that it doesn't remove anything that's not there, and therefore, in the end, after removing 3, we still have 1 edge left, which is this one. Now, to use exactly the same program, but with the adjacency matrix representation, gives us this output. It's exactly the same output, but as we will see, the show graph and all the operations have been implemented very differently, namely with the help of an adjacency matrix. And then there's the third implementation, which uses a list, and you can see it not only compiles the list of edges, this is the adjacency list implementation, but it also uses a linked list implementation to generate this. And the way this outputs a graph now really uses the displaying of the adjacency lists. So you see that after inserting these 3 edges, these are the adjacency lists for every node. And after removing 2 of the 3 edges, all we are left with is the 1 edge between 3 and 4, which is represented as 2 vertices in adjacency lists, 4 in the adjacency list for 3 and 3 in the adjacency list for 4. Now, let me just show you very quickly the array of edges representation. It just uses the idea of an array of edges and implements exactly the operations that we looked at in pseudocode. In particular, here I'm using a symbolic constant enough. Remember, I've said we have to allocate enough memory, and you have to somehow define what we mean by enough. This is quite arbitrary here. Then there's enough memory that is being allocated, and inserting an edge and removing an edge is the operation on the array of edges that has been implemented here. This is not the one that we will be using for the rest of this course. This is why I'm going through it very quickly. What we will actually be using, and this is why I'm going to show that in slightly more detail, is the adjacency matrix implementation in C. This is the just repetition of the adjacency, the edges representation. And what I've done for that implementation is to use a struct which contains the basic information plus the keeping track of the size of the edge array in order to make sure that I'm not overflowing that array. And then I have an array of edges being allocated. Now the adjacency matrix, this is the one that we will be using. The representation in C looks like this. We have the graph rep itself, which counts the number of vertices and edges, and has a pointer to an array of vectors for every row in the adjacency matrix. And the size of these rows are fixed. If we have 4 vertices, then we will have a 4x4 matrix represented here. So that's the 2-dimensional adjacency matrix representation in C, and this is represented with the help of this struct. Now, having a quick look at how this is actually implemented in C, if we build a new graph, there are a few things that I'm asserting. I'm stopping the program immediately if someone asks for a negative number of vertices. Then I'm allocating memory for the graph representation itself. That is for this particular struct. Then I'm allocating memory for all the rows. individually, and then I'm allocating memory for these arrays that we see here. So this is what happens here. First of all, I allocate space for the graph representation itself, which had these two fields, NV and NE, which are initialized as you would expect. Then I'm allocating the edge array, one pointer for every row. That's why I have V here times the size of an integer pointer, as always making sure that this does not return null, so that I get the space that I'm requesting. And then for every vertex, that's what I'm doing here, I'm allocating space for exactly V integers for every column, one integer. I'm using a nice trick here, namely instead of using malloc, I use calloc, which is another standard function that is provided by standard lib and has the advantage that it not only allocates memory, but initializes everything by 0, which is exactly what we have to do for a matrix when we initialize it, so that I don't have to add these two for loops that would initialize the elements by 0 themselves. Now, what's a bit unusual and unfortunate is that calloc works slightly differently in terms of the parameters than malloc. Rather than just providing the number of cells or bytes that you want to allocate memory for, you actually have to say how many elements you have and what type they are, so that this takes 2 arguments. Now, the reason for this is that in order to know where to put the zeros, it distinguishes between this size and the V, where the zeros have to be put to. Although in the end, it will be 0 everywhere. It's just the internal implementation that requires this. So make sure that when you use calloc, that you don't use just one argument, but that you divide it into the size of every individual element that needs to be initialized by 0, and then the number of these elements that you need.
Does that mean it would only work for structs that have integer types defined in them?
No, not at all. So you could also say size of character here, and it would then initialize a string of like 7 characters with zeros. It's just the reason for doing this is initializing a single byte with 0, which corresponds to a character, requires a slightly different internal operation than initializing a 4-byte integer with 0. It would just be faster to do it. Instead of allocating every single byte, there's other operations that allocate chunks of bytes to 0. And that's why you distinguish it. But you can put in any type that you want here. So it really is the same as malloc. That's this. Then inserting and removing an edge is extremely simple, as we know with the adjacency matrix. Here I'm adding, just to be on the safe side, another assertion that when someone wants to insert or remove an edge, then the graph itself must exist. And I'm also checking whether I'm trying to remove or add a valid edge. That is an edge where V and W have been assigned numbers that satisfy this definition here, namely that the vertex number is greater than 0 and smaller than NV, which is the number of vertices that we have. And this is nice to have whenever I'm using this graph abstract data type and I'm a little careless and I haven't initialized an edge properly, for example, then it always tells me with this assertion that I'm trying to insert something that doesn't exist. And of course, it also makes sure that I'm not overwriting memory that I can't really access. Then inserting an edge and removing an edge just means to set the Boolean values to either 1 or 0. That's straightforward. And checking neighbors, assuming an adjacency matrix representation. This is what I also had to implement for this. I've put that here as an exercise, but I think this is so simple. It's just the adjacency matrix. You have to check whether in the matrix there is a 0 or a 1. So I might just show you the result. It, again, asserts that what I'm asking for does exist, and then it only checks whether there is a 0 or not. If there is a 0, then the answer is no, and if there's a non-zero value, a 1 in the Boolean case, then the answer would be yes, the two vertices are adjacent. Let me just quickly show you that this is exactly what I have implemented here as the graph.c. So when you go to the web page for this course and you look at the programs for tonight, then you will see there's one program, graph.c, which does implement the adjacency matrix representation. I thought it was here, but it was actually here. This was the one thing that I had to point out. I mentioned earlier that I always want to use the type bool. Now, to make very clear that the return type is actually integer but should be interpreted as true or false, if you want to do that, then you have to include this library function standard bool.h. And you will see that I'm doing this from now on in almost all programs. In every program where I want to use bool, I'm including this header file. So apart from that, this is just using the program that we have seen. And I don't think there's anything different from what we had on the slide. Valid v, inserting an edge, removing an edge. Adjacent is what we just saw. Showing a graph does use the two loops. And here I'm actually running to g nv minus 1. I should have put in nv minus 2, but it really doesn't make a difference because if this is nv, then the second loop will not be executed at all. And freeing a graph means to, first of all, free all the rows individually, and then free the array of pointers to the rows, and at the end, free the graph struct itself. And to finish that, here's the implementation for the adjacency list representation. Now, the way this is done here is, first of all, the struct is exactly the same as in case of the adjacency matrix. I do have a counter for the number of vertices, a counter for the number of edges, and a pointer to the structure that contains all the adjacency lists, which consists of an array of pointers, one for every node, just like in the adjacency matrix implementation. But now we don't have rows of fixed size, but we do have linked lists. And this is why I'm using a struct node, which implements a simple linked list of vertices, which just has the number, the name of the vertex, the name of the vertex, and a pointer to the next element in that linked list, which ends with a null pointer to indicate the end of that list. Now that's what I have implemented as the adjacency list representation, and you can find that, as we have seen on the computer, on my computer here, also on the web page under the program adjacency list .c. A simple exercise: if you have a linked list, how would you implement a function to check whether two vertices are directly connected by an edge? So that function bool adjacent, you are given a graph and you want to check whether x and y are adjacent. How would we do that with the adjacency list implementation? Let me just quickly go through this. This is the adjacency list implementation. It includes an abstract data type list, which is just an implementation, our standard implementation for a linked list for integers. Now, how do you think I have implemented the function adjacent in this module? Yes, that's exactly right. You choose either of them, either X or Y. You access the linked list, and then you do a search in that linked list. And this is precisely what I have done here. If I'm looking for adjacent, then all it does is it takes the standard function inLL, which checks whether a particular element is in a linked list. It takes, in this case, the linked list for node V and checks whether W is an element in that linked list. So that's the graph list of edges, which is probably not the best name for it. I should have called it adjacency list. I'm probably going to change that as well, but you can look into that program and then see exactly how this is being implemented with the help of a standard linked list implementation, which uses just our standard linked list operations. And that completes the introduction to the graph data structure and how we can represent it. And then I'll have another short break, and then we will be looking at the first very fundamental problem, namely searching whether two vertices are connected based on any implementation of a graph abstract data type. Okay, short break. And well, it's good that we are through this introduction to the data structures because now we can actually look at interesting problems to solve with the help of these different implementations. And this is probably less dry and a bit more interesting to look at algorithms, how to deal with these data structures. So that was the one slide which shows you that in order to check adjacency with a linked list, you just use the standard operation to go through a linked list and check whether it contains a particular element. Now, the first problem that we want to look at is graph traversal. And can I get everyone's attention? We will be asking the question, how can we find paths? Now, a simple question on paths is there a path between two vertices, which we can call source and destination? We might be interested in not only the question yes or the answer yes or no, but we might want to know what is the sequence of vertices from source to destination, so that we know there is not only a path, but we get a path. The approach to solve this problem is to start at the vertex source, then examine all the vertices that are adjacent to source. If any of them is the destination, then we're done. We have found the path. We can say yes. Otherwise, you try vertices that are two edges away from source. And you repeat looking further and further from source until either you find the destination or you can be sure that you looked at all the vertices and you know that there is no path between source and destination. Now, there's generally two very basic and principled strategies for graph traversal and for search that are known as depth first and breadth first search. Depth first, or DFS, follows one path to completion until a dead end or until you have exhausted all possibilities without running into cycles before considering others, whereas breadth first search in a certain sense fans out from the starting vertex, spreading or generating a spreading subgraph. This is probably easiest to see with an example like this. Suppose this is the graph that we have. It's the same in both cases. And our task is to check whether there is a path from A to H. What we would do with breadth first search is we would first of all look at all nodes one edge apart from source, which is B, C, and D. And if we do it in alphabetical order, then we would look at B first, then C, then D. None of those is our destination. So we would then continue to look at nodes that are two edges apart from A, which would be E, F, and G. Again, we don't find the solution here. So then we go to the next nodes that are three edges apart or away from A. And the first one we would be looking at would be going back to the first node that we have here and look at adjacent vertices. The answer would be yes, because we found H here. And then the path that would be returned would be A, B, E, and H. Now for depth first search, it would work very differently. We would go deeper and deeper until we reach a dead end. And then we might try alternatives. So here we look at, if we do it in alphabetical order, look at B first, then C. We could also go to E, but C comes first. Then to D. Another option is we can't really go to A. We should remember that we've started at A, otherwise we would run in circles here, and that wouldn't get us anywhere. We could also go at F, but if we do it in alphabetical order, we would first of all go to D and continue from there. Go to G, which means that from here we can't continue, because all we could do is go back to D, but we've been there already. So we look at nodes on the way and see whether there are still alternatives that we haven't explored yet. And continue our depth first search here with F. And from F, we have the choice between H and I. And we would choose H first, because if we follow alphabetical order, this would be the first to explore. and then we found our destination. Now, what would be the path returned by this search? It would be the path that we took here, A, B, C, F, and H. And you can see that these two different search methods might very well give you the same answer, of course. It's yes in both cases, but it might give you different paths. And what is important is that in both approaches, you ignore some edges by remembering previously visited vertices. Otherwise, you would, as I said, run into a cycle here, and then the algorithm wouldn't terminate. So that's the basic principle, breadth-first search versus depth-first search. Let's first of all look at depth-first search, because that is easier to implement recursively in particular. It's a very simple algorithm. You depth-first search, you want to get from you want to explore a graph using that depth-first strategy. Starting at vertex V, you mark V as visited, and then you look at all the edges, all the adjacent vertices W, adjacent to V. If W has not been visited already, just to avoid running into a cycle, you would then continue your depth-first search with W. This recursion does induce backtracking, and by backtracking, I mean that if you end in a situation where there is no more adjacent edge, adjacent vertex that has not been visited, then this recursion terminates at this point, and you would go back to the previous level where you might have other edges to look at, other adjacent vertices, and you would continue with those in that recursion. And you can easily see this recursion to D, then to G, and here you wouldn't have any adjacent vertex that hasn't been visited. So the recursion would terminate here because there's no other possibility. Here there was only that one possibility to go to G, so that would terminate the recursion at this level, and you would then go back here and continue with the for each loop to go to F and to H. Now this is what is known as backtracking. You end in a dead end, and then you backtrack to the last choice point where there are still choices left. This is what this very simple algorithm does, and we can implement this or describe it with that pseudocode in a little more detail. We are now trying to solve the question, is there a path from source to destination? And it does that recursively by calling that function DFS path check, which is recursive. From a given point, which at the beginning is the source, tries to find whether there is a path to that destination. And the way it does that recursively is, first of all, it marks V as visited. If we have found the destination, it returns true. Else, it tries all the edges outgoing from V, and only for those nodes W that have not yet been visited, calls the DFS path check recursively. And if that says yes, then we know that we have found a path from V via W, because this is now where we went to destination. And if there is a path from W to destination, and we have an edge from V to W, then obviously we also have a path from V to destination. If we have exhausted all these possibilities and we don't return true, then it means there is no path from V to destination. Let's have a quick look at how that would work with this particular exercise and see how the algorithm would work. I've got that same graph here. Let's go back to this algorithm that might make it easier to actually check what is going to happen. Now we want to see whether there is a path from 0 to 5. What would we have to do? We start the recursion with v is 0, the destination is 5. And the first thing that we do is we mark 0 as visited, so that would get a tick. And then which node would we consider next? We would go to 1. 1 has not been visited, so we call the function recursively with 1. With 1, we tick this. This is the first thing that happens. Mark 1 as visited. This is not our destination. We are looking for 5. So what's the next vertex to consider? It would first of all be 0, but 0 doesn't satisfy that check that 0 has not been visited. And therefore, the next node to visit would be 2. We would mark 2 as visited. And, well, it's very clear what we have to do. We can't go back to 1 because it has already been marked. We have the choice between 4 and 3. But if we do that systematically with that for loop that we see in that algorithm, then the next one would be 3. We mark that as visited, then 4, and finally 5. And then the answer would be yes. You see that that was a bit difficult. We could have said that we can go from 0 to 5 much faster. And with breadth first search, we would actually, as we will see later, look at 1, then at 4, and then at 5, and the answer would immediately be yes. But depth first search really, in this case, requires us to take that detour, but we can be assured that the answer will always be correct. Now that's what we do with the recursive DFS path checking. And I can quickly show you that that also is a program that you can find on the course webpage. This is the DFS recursive. And there's absolutely nothing surprising in here. Nope, I don't want to show this at this point because it actually contains more than what we have talked about so far. And that is, this is what we've just done. This is the answer that we get. And what we will look at next after a quick look at the complexity is to actually generate that path. This is what the algorithm hasn't done yet. And the program that I've implemented actually does that as well. A quick look at the cost first. What we have to do is, as we've seen, we have to visit each vertex in the worst case at most once, if we make sure that we don't run into cycles. So the cost is linear in the number of vertices to visit these vertices. Now, what that loop also requires is we have to visit all edges that are incident on a particular vertex that we're currently looking at. And the cost to do that is in total linear in the number of edges. In the worst case, we really have to look at all the edges in the graph. Now that is actually true only if we assume an adjacency list representation. So when we then take the combined complexity of this algorithm, the answer is it is linear in both the number of vertices and in the number of edges. But this answer is only correct if we use an adjacency list representation. And why is that? Remember that this algorithm does have this for loop. You have to go through, whenever you visit a vertex, in the worst case, all the edges adjacent to that vertex. And if we have to visit all the vertices before we reach the end, then in total we have to visit all the edges in the graph. But this for loop alone might be taking more time if we have a different representation. In particular, if we look at the array of edges representation, if you're looking at just one particular vertex, and you have to execute this loop for all edges that are incident to that vertex, then the cost will in total be e squared, because for every vertex, you might, in the worst case, have to go through the entire list or the entire array of edges. And you may have to do that every time. And this is why you have to do that e times e if you have to visit every edge. And visiting every edge requires you to every time go through the list of edges. And this is why then the cost of depth first search for this representation is much worse. Instead of v plus e, it would be v plus e squared. This is the array of edges. If we look at the implementation that we will be using, the adjacency matrix representation, then implementing that loop to find all the edges outgoing from V would require to go through the entire row of the adjacency matrix. And that requires OV for every individual vertex. And if we have to visit all vertices on our path to the destination, then we have to do that V times, so that the complexity, the cost, will then be OV squared, just to implement this loop for all edges that go out of V, and do that for all vertices. That is for the adjacency matrix representation. The cost of depth first search will be OV squared. And that goes to show that you don't have a straightforward answer to how complex a particular algorithm, even a simple algorithm like that depth first or very basic algorithm is for graphs in general, because that depends on the actual representation. Now it's become custom when you ask someone what is the complexity of depth first search, to always assume the most efficient representation. So if then someone says OV plus E, then that assumes that you have the most efficient representation for this. What we can also see is that for dense graphs, it doesn't really make much of a difference, because for dense graphs, we know that the number of edges is roughly of the size of V squared. And if that is the case, then OV plus E is actually the same as OV plus V squared, which is the same as OV squared. So for dense graphs, OV plus E is actually of the same order as OV squared. And then it doesn't make a difference whether you do this analysis or the analysis on the previous slide. Whereas for sparse graphs, the order or the number of edges is typically in the order of the number of vertices. And then OV plus E is just O of 2 times E, which is the same as O of E. And then you see, really, it does make a difference. In both cases, this is depth first search for the adjacency list. For dense graphs is the same as for the adjacency matrix implementation, whereas for very sparse graphs, it's linear in the number of edges. And that again goes to show you that depending on the type of graphs that you're looking at, you might end up with a very different complexity or runtime behavior of a very basic algorithm like this search algorithm. Now back to the question that I've actually implemented here. Knowing whether a path exists, where we just got the answer yes or no, there is a path from source to destination, we might want to extend the depth first search so that we know what the path is. And this can be very nicely added to the recursive implementation by recording the previously visited nodes as we search through the graph, and then just recording where we came from, so that in the end we can trace back the path, and ultimately in this way recover the entire path from source to destination. For this purpose, we can use that array visited, which actually you would have used anyway to mark whether a vertex has been visited or not. But now you're not marking just yes or no, but you actually record where you came from to visit. a vertex, and that alone suffices to, in the end, recover the path. So that's the algorithm down here. It's the same as before, but now recording where we came from, and in the end, outputting the path that was found. Now, at the beginning, we initialize the visited v to -1. Why not 0? Because 0 is an actual node where we might have come from, as our nodes are numbered from 0 to nv minus 1. So I'm using here a number that definitely can't be a predecessor on the path. And then I'm saying that I didn't come from anywhere if I start at the source. And this is also how, when I unwind the path in the end, I know that I have reached the beginning of the path. Then I've got the recursive call that we will be looking at further down this slide. And if that returns true, that is, there is a path from source to destination, then I'm unwinding the path back from destination to the source. That is, I start at the destination, and through that while loop, until I have reached the source, I'm printing the vertex, which would be first the destination vertex, and then I look at where I came from to the destination vertex and set this as my new v. So I'm looking at the predecessor for the destination, and then I'm looking at where I came from to the predecessor. And in this way, I'm just walking back the depth first search until I have reached the source. The depth first search recursion is the same as before. If I've reached the destination, then I just return true. Otherwise, for all the adjacent vertices, if this vertex has not been visited before, and I know this when it still has this initial value of -1, the array for this vertex w, then I record where I came from. This is what I need in order to recover the path in the end. And this is all I need to do. And now this visited w equals v has the second purpose of marking this vertex as visited. As soon as it is no longer -1, I know that I have been there. And this is all I need to do in order to extend this algorithm to not only return yes or no, but to use this visited array to give me the path that has been found. And we can look at how that would work for this particular example, a slightly more complex graph. Question is, again, what would happen if we do depth first search, now with the goal of finding the path and not just returning yes or no. It's a bit more interesting than the example that we looked at before. So here we want to go from 0 to 6, and we want to see what the path is that is being returned by our depth first search. So if we look at this algorithm, the first thing that, or the algorithm on the previous slide, the first thing that happens is that this visited array will all be initialized by -1, indicated by the question marks here. And now the question is, what would happen first when we do apply this algorithm? So let's try to find a path from 0 to 6. And let's apply this recursive procedure. We call it with the starting node 0. And then, actually I should say that 0 would be initialized by 0. This is in fact what happens here even before we call the recursion. And then what happens next? We check whether 0 is the destination. Of course, it isn't. So then we go through all the edges from 0. And doing it alphabetically, not alphabetically, just in order, we would go to 1. And what would we change in that array? Yeah, actually I can probably overwrite this here. So this 1 will get a 0, because this is where we just came from. And what happens next? So we are here, 5. And what would be put in here? 5 is 1, because this is where we came from. Now, with 5, we have several choices. We could go to 0. But 0 is no longer minus 1, so we can't go to 0. Therefore, we go to 3. And therefore, 3 gets 5. And then we are here. What's next? 2. So we put in a 3 here. And then? Then we can't decide here or here. Actually, we can't go here because we've been here. There's no longer minus 1 here, and we can't go here. So the recursion at this point for node 2 ends. And this is why we go back to the previous recursive call, which came from where we came from here. Now here we looked at 2. What would we look at next? We would look at 4. And therefore, 4 would also get 3 here. Then we are at 4, and where would we go next? Yeah, we can't go to 5 because we've been there, so we would go to 7. 7 will get a 4. And you see that with depth-first search, you're really getting away from that 6 where we actually wanted to go to, but this is what happens in depth-first search. Now we are here, then 8, where we came from 7. 9, where we came from 8. And so 9, we can't continue. We've been here. 8, there's nothing to do. 3, 4, 7, we already had. We were, where did we come from? 7. Can't go back to 5. 9, we already saw. So back to 4. No other choice here, so finally we go back to 5. And at 5, we had one other node left, which was 6. So this will get 5 also. You see, actually, to find that relatively short path, we had to go through all the nodes. But the good thing now is, what is the path that we have generated? And this is very easy to recover from all the numbers that we've inserted here. We wanted to go to 6, so we print out 6 first. We came from 5. So we print out 5. 5, we came from 1. And 1, we came from 0. And we can stop. So this is quite nice. With that visited array, we have now a way of, although we have visited all these paths, we know that this is the actual path we took through depth-first search to reach that 6, and we can print out that path in this format by just rewinding the path that we took. Now that is, why am I doing this? But this probably doesn't make much of a difference. This is now what I've implemented here. This is the breadth-first search recursive with the path recovered through that visited array. And you can see that this recursive function does record where we came from. And other than that, it just does the same as before. It uses the graph abstract data type to check adjacency and whether a node has been visited before or not. This doesn't do much here. And this graph that I have here, this is actually the one that we had earlier, where we took that long detour from 0 to 5 instead of directly going from 0 to 5. And then this outputs the path in the exact same way as we have just done. This is the program DFS recursive, and the same makefile that I've used before and that you can find on the course webpage also makes DFS, the depth first search, this DFS recursive, with the help of that graph abstract data type that you can see here. And if you run it, then it gives you this long path for that graph that we had earlier, which was this one. And we really had to take that detour from 0 to 5 via all these other nodes, and this is what is being returned here. Now, I didn't get just as far as I wanted to. We still have to look at breadth first search. The effect of this is it's just a few more slides, and we will do that obviously next week. The effect is that there's one exercise on the homework that you should be doing next week, namely checking your understanding of breadth first search and depth first search. In fact, you can start with depth first search already, but wait until next week with this particular exercise. That completes the introduction to graphs. If you want to read more about it, here's a summary of what we talked about today, not yet breadth